others will be more. Each time we wash away, we bounce back to the shore. We know we lead the way, keeping odds at bay. See the sunrise tomorrow, inspire the world to follow.
Okay, myself Sumanto Kundu, Assistant Professor of Electrical Engineering Department. Today in the subject code of EE 501, that is Electrical Machine 2, we are going to start our lecture number 13, that is on the topic development of equivalent circuit of single phase induction motor. So this is my objective, to develop the equivalent circuit of single phase induction motor. Okay. So till now, whatever we have taught in our single phase induction motor theory, we have seen that single phase induction motor can be described, the principle of operation, the operation of single phase induction motor can be described by double revolving field theory. So using double revolving field theory, we can explain the operating principle of single phase induction motor. And we have seen that in case of single phase induction motor, there is a production of pulsating magnetic field. There is a production of pulsating magnetic field. And according to double field revolving theory, this pulsating magnetic field can be comprises of two different fields. One is called forward field and one is called backward field. So that we have seen that this pulsating magnetic field, what is produced inside the stator of a single phase induction motor, is a combination of these two fields. One is forward field and another one is backward field. Both are rotating at synchronous speed ns. Both are rotating at synchronous speed ns, but in opposite direction. If one is rotating in anti-clockwise direction, the another one is rotating as clockwise direction. So if one is clockwise, the another one is anti-clockwise direction. Again, this double revolving field theory explain why there is no starting torque of single phase induction motor. And it also explain that if by means of some auxiliary means, if we can provide the initial inertia or initial thrust to the single phase induction motor rotor, it will start rotating, and after some time with the rotor speed nr, stable speed nr rpm, it will start rotating. So this is what we have seen. Okay, so let me go to the slide now. So we have mentioned this that say equivalent circuit of a single phase induction motor can be obtained by two methods called, one is double field revolving theory and cross field theory. But here we are develop the equivalent circuit using double revolving field theory, that is only when the main winding is energized. Similarly, by using cross field theory, we can also develop the equivalent circuit of single phase induction motor, but in that case we have to use the symmetrical component analysis, and which is not in the scope of our syllabus. This is for higher study, so we are only concentrate, or we will only limited our study into the double field revolving theory. And the pulsating field can be produced, can be a combined effect of two oppositely rotating magnetic field stator. I have already told this. And next point is double revolving field theory explain the absence of starting torque in single phase induction motor, also I told. And this is also explain how the motor continues to rotor when it start by some auxiliary method. It also explain how the motor continues to rotate when it is start by some auxiliary method. And then now, for the development of equivalent circuit, the single phase induction motor can be considered as a combination of three phase motor whose stator are connected in series and rotor are mechanically coupled. So, if we consider a single phase induction motor, then that single phase induction motor can be described by two series combination of three phase induction motor, because the pulsating field which is produced inside the stator can be thought of combination of two field, one is forward field and one is backward field, and both are rotating at same synchronous speed ns but in opposite direction. Okay, and one more thing, the total number of turns of single phase winding, stator winding, if n1, then these two phases of the stator winding that will represent the single phase induction motor are half of the total number of turns. Okay, and one more thing, to represent one motor in forward rotating field and the another motor is rotating, three phase motor is representing the backward rotating field, where the number of turns are the half of the total number of turns of single phase induction motor. But in the same time we have to keep one thing in our mind, that if the one motor is rotate in clockwise rotation, then the another motor is rotating in anti-clockwise rotation, and that is only possible when the phase sequence of the supply of the two motors which is we are applying to the stator winding are different. Then only it will rotate, one is forward direction, another one is backward direction. Okay, so that is what we have to keep into mind, that phase sequence of the supply of the three phases of the two stator must be opposite. So if we now look into the picture, so this is the picture. So this is the pictorial representation of a single phase induction motor. This is my rotor and this is my single stator winding, and as this single phase induction motor double field revolving theory explain that it is a combination of two field, one is forward, one is reverse, so it is represented by two combination of stator winding and the rotor are magnetically coupled. And look here, the total number of turns is n1, whereas in these two representative three phase winding the number of turns are N1 by 2 each phase. And if this is A phase, this is C phase, and this is B phase. But look, the phase sequence is different in this two stator winding, because if you see, A is connected with A, but whereas C is connected with B phase, and here the V phase is connected with C phase. So if one is rotating in forward direction or clockwise direction, the another one is rotate in anti-clockwise direction, but the both speed are same ns. So this is the equivalent circuit of single phase induction motor with two series combination of three phase induction motor, and magnetically coupling exists between the rotor. Okay. Now equivalent of single phase transformer. Now we have seen that single phase induction motor equivalent circuit development is started with the representation of single phase induction motor by two equivalent three phase induction motor whose stator are series connected. And when we have studied three phase induction motor, we have seen that three phase induction motor equivalent circuit is similar to the equivalent circuit of the single phase transformer at standstill condition. That means when the rotor is not rotating, it is on the verge of rotating, that means it is in standstill condition, we can consider single phase induction motor or three phase induction motor similar to a single phase transformer in short circuit condition, as if the secondary is shorted. So the equivalent circuit of single phase induction motor can be represented by the equivalent circuit of a single phase transformer in short circuit condition. Okay. So this is the representation of a single phase induction motor. But one thing we should see in this equivalent circuit, that is, whenever we have studied the equivalent circuit of single phase transformer in short circuit condition, we have seen that there is no shunt branch parameter exist. Only the series branches are exist because it is shorted, so the whole current will pass through this secondary terminal, so no current will pass through this shunt admittance or shunt resistance branch. But whereas in case of single phase induction motor, there is a JXM reactance band is present to represent the magnetizing current of a single phase induction motor. Now the question that must spring up into our mind, that whenever we have discussed the single phase transformer in short circuit condition, we have neglected the shunt branch parameter, whereas when we are discussing the single phase transformer, we are considering the reactance branch. So why? Because in case of single phase transformer, the magnetizing current is very less, whereas in case of single phase induction motor, it is 30 to 40% of the full load current. So the higher value of magnetizing current forced the equivalent circuit to consider this shunt branch as JXM. So this is the equivalent circuit of single phase induction motor whose secondary or rotor are shorted, because rotor is in standstill condition, means rotor is not moving, so rotor is standstill, means rotor is shorted, similar to the single phase induction motor at short circuit condition. Now, what is the difference of the equivalent circuit of single phase transformer? That is, we have discussed so far. With that, in terms of magnetizing current concern, there is the only different exist. Okay, so this is the difference. So here the shunt branch parameter are absent in case of single phase induction transformer in short circuit condition, but where in case of single phase induction motor it is always present to represent the higher value of magnetizing current. That's why that JXM parameter is exist. Now modification in equivalent circuit based on double revolving field theory. So what modification can be we have done? So before we proceed further into the details, we should consider too much nomenclature things. That is, here the R1 and JX1 is the stator side impedance, and R2 plus JX2 is the secondary or rotor side impedance referred to the stator. And where is E is the back EMF. E is the back EMF induced in the stator winding by the action of pulsating magnetic field. This is the back EMF produced in the stator due to the pulsating magnetic field. Now, although here we have represent the shunt parameter in our circuit of single phase equivalent circuit of single phase induction motor, but still the core loss is not present in case of induction motor, because whenever we have studied the three phase induction motor equivalent circuit, we have seen that core loss is assumed to be constant and during the operation, and it is added along with this rotational losses. So it is lumped with the rotational losses, and the total losses is represented by this shunt branch parameter. So although it is exist here, but the core loss is constant throughout the operation. So now we have seen earlier when we have discussed in our from lecture number 1 to till now lecture number 13 that pulsating magnetic field of single phase induction motor can be considered as combination of two field. One is forward field and another one is backward field. Both are rotated at synchronous speed ns but in opposite direction. And when we have studied that double revolving field theory, if we recall, we have seen that the magnitude of both the field are same. That is, for both the field, phi f equals to phi b, and which is the half of the total value of the pulsating field. So that is what we have seen in case of the derivation of or analysis of double revolving field theory, that the amplitude of both the field are same but half of the amplitude of the pulsating field. So now if we merge these two concepts, that the magnitudes are same and half of the pulsating field, and single phase induction motor can be considered of a combination, two series combination of two three phase induction motor. So we can represent the previous equivalent circuit, this equivalent circuit, as a combination of two similar equivalent circuit where the amplitudes or parameters are same, only the value of rotation is different. Okay, so that we can done. So that is we have implemented. So we have decomposed that standstill equivalent circuit of single phase induction motor into two different circuits, one representing that forward magnetic field EF and another one is backward magnetic field EB. And look, all the number of turns, as we have discussed, that single phase induction motor is a combination of two series combination of three phase induction motor where the number of turns are half. So all the parameters we are made half. So it is V1 by 2, V1 by 2, it is E by 2, E by 2, and all the rest parameters are, we have made the half value. Now, so now we are proceeding towards the overall equivalent circuit. So now we can describe earlier that we can represent that this is as a series combination of two three-phase transformer. So we have done here the series combination of the two circuits. So we have made a series connection, and we have rearranged this circuit to this way, where this upper parameter are become here and rest of the thing remains same, and later on we have added up these two series parameter, that R1 by 2 plus R1 by 2, it is become R1, and GX1 by 2 and GX1 by 2 will become GX1. So the next modification what we have done is this. So this is which we have done. Same thing, we have added up these two parameters, so this will become, and we have rearranged a little bit, nothing else we have done, just a pictorial different orientation we have done. And so this is the equivalent circuit of single phase induction motor at standstill condition. Okay, now in running condition, in running condition what will happen? Let me check what will happen in running condition. Now we have seen by through auxiliary means, if we give the initial inertia to the rotor of the single phase induction motor, it will continue to rotate in that particular direction at a stable speed in R, that we have discussed so far. At a stable speed in R, it will start rotate. Okay, in R RPM it will rotate. Now but the speed of both the field is same. It will rotate at synchronous speed ns, stator field. Okay, so now once it achieves the speed nr, what we will do, we will cut that auxiliary field from the circuit, and only the main winding remain under running condition. There is no auxiliary winding remain once it start rotating in a single direction by some auxiliary means. Okay, so under such condition, if we take the forward slip as S, forward rotating magnetic field, S equals to ns minus nr by ns. Okay, so what will happen with the backward rotating magnetic field? The backward rotating magnetic field is ns minus of nr in opposite direction by ns. So that means ns plus nr by ns, that is 2ns minus ns minus nr by ns, that means 2 minus ns minus nr by ns, that is 2 minus s. So where the slip of forward field is s, the backward field rotate at a slip 2s. Now when we have discussed that equivalent circuit of three-phase induction motor, in running condition we have seen the rotor resistance is the variable parameter, because this R2 by S represented the electrical equivalent of the mechanical power developed in the rotor, because here the electrical energy is converted into mechanical energy. So in case of single phase induction motor, the variable parameter will be the resistance in both forward circuit as well as in the backward field representative circuit, whereas the current which is produced in the forward field, it has a frequency of SF, whereas in the due to backward it will be 2 minus S by F. So these are the slip frequency at which the rotor current induced in that equivalent circuit. Okay, so this thing only we have to incorporate in comparison to that equivalent circuit of this standstill condition. That means here R2 by 2 it will become R2 by 2S, and here R2 by 2 will become R2 by 2 into S minus 2 minus S. So this slip term will appear here in the resistance, and this will represented by a variable resistance to represent the mechanical power, electrical equivalent of the mechanical power developed. Okay, so in running condition, if we draw the equivalent circuit, it will be it will be R1 will be there, X1 will be there, and then there will be a JXM by 2 here. So this is R1, this is JX1, this is current I1, this is JXM by 2, and here it will become variable resistance R2 by 2S, and this will become JX2 by 2. Okay, similarly for backward it will be these things, and then these things, and here's the similar thing. Here it will become R2 by 2 into 2 minus S. Here it will remain JX2 by 2. This will become JXM by 2, and this is the equivalent circuit of single phase induction motor in running condition. This is my EF, this is my EB equals to E by 2 equals to E by 2, means this voltage, this voltage, this voltage. Okay, so this is the representation in running condition, and this combination of R1 plus JX1 is called Z1. Z1 equals to R1 plus JX1, and this is ZF. So ZF equals to RF plus JXF, and this is equals to half JXM by 2, and this is in parallel with the series combination of JX2 by 2 plus R2 by 2S. Okay, similarly this is represented by backward impedance ZB. So ZF and ZB again depending on the relative speed of the rotor. So ZB will be RB plus JXB, where RB and plus JXB that can be represented again JXM by 2 in parallel with the series combination of R2 by 2, 2 by S plus J plus JX2 by 2. So let me write it here properly again. So my ZB will be my ZB will be RB plus JXB, that is equals to this JXM by 2, JXM by 2, and this is in parallel with this series combination of JX2 by 2 plus R2 by 2 into 2 minus S. This is in parallel with that R2 by 2 minus S plus JX2 by 2. So this is my the simplified equivalent circuit of single phase induction motor in running condition. Okay, so this is all about the equivalent circuit of single phase induction motor. So basically if we sum up the total class of my today's class, it will be that a single phase induction motor is represented by double field revolving theory, its operation, because we are not considering here cross field theory. And according to double field revolving theory, there is a forward field and backward field whose magnitudes are same, both are rotating at same speed but in opposite direction. So the equivalent circuit can be represented by two different circuit. Again, single phase induction motor can be represented by a series combination of two three-phase induction motor whose stator are series connected and rotor are magnetically coupled. So again, that two circuit we can connect it in series, and then we can simplify it. So if we simplified it, it will turn into in this figure, which is the equivalent circuit of single phase induction motor in standstill condition. One thing we have to keep into mind: in forward field the slip is S, in backward field the slip is 2 minus S, and as we have seen in the development of single equivalent circuit of three-phase induction motor, that resistance part is represent with variable thing, because that electrical equivalent of the mechanical power developed representation. So here also it will become a variable thing, with the slip part will incorporate here in running condition, and that is what actually we have done. Here it will be a S term will appear, and here it will become a 2 minus S term will appear, and rest of the thing will remain same. So this is all about today's class. So these are the few references which helps us to develop the equivalent circuit. Okay, and thank you very much.